In the last video, I explained why we are creating a new offline first web framework. In this video, we will take some crucial decisions such as designing the project architecture, deciding the tech stack we will be using, and finally, we will start developing the project by setting up a base web server. Let's start with framework architecture. I've already created a high level architecture diagram and divided that into two layers, server layer as well as client layer. In server, we will have core engine that will be responsible for plugin system, doc type engine, auth and permission, etc. Then we will have API gateway that will be responsible for API server, WebSocket gateway, etc. Then we will have data layer that will be responsible for handling data as well as syncing the data. And we will have infrastructure management that will be responsible for multi-site management, file storage, etc. In the client side, we will have UI layer that is responsible for front-end runtime, component system, as well as the UI builder. Then we will have client-side offline first data section that will be responsible for managing the local database, the sync engine, and conflict resolution. Then we will have API client that is responsible for communicating with the API server. With this, I have also created a data flow diagram for the local first design. Here the framework will always have a local database and it will be synced from a server database. The local database will be always used for the user actions such as create, read, update, delete, etc. It will be done using local SQLite database, and all the UI updates happens instantly. So whatever change needs to happen, that is pushed to an offline queue that will be synced with the server database. In the server database, we will have a sync coordination system. Then there will be a main data store, for example, PostgreSQL. Then in the server database, we will also have some background processing section. For syncing the local database to the server database, we will use a system such as Electric SQL so that all the update happens in real time. Before going ahead with the project structure, let's go through the tech stack decisions so that you will understand why I structured the project the way I did. Let's start with the big one, that is programming language. I considered using Rust or Golang, but after a lot of research, I'm going ahead with JavaScript and specifically with Bun.js. And let me explain why. First is the ecosystem. Whenever we need a specific library or tool, it probably already exists in JavaScript ecosystem. It might not be the same with Rust or Golang. And more than that, we can use same language on the client side as well as server side. That is the biggest one. And also developer adoption will be more with JavaScript when compared to Golang or Rust. Another big advantage of using Bun.js is it is not just JavaScript runtime, but it also has some built-in tooling such as bundler, test runner, package manager, etc. so that we don't need to use separate tools for different tasks. Also, to compare how Rust, Golang and JavaScript in Bun environment perform against each other, I have created some benchmark scripts. Let's see how they perform. So what I have done is I created simple HTTP servers using Rust, which runs on port 7000, and Go, which runs on port 8000, and TypeScript, which runs on port 9000 using Bun's default HTTP server. So to run this, what I have done is I have compiled this into single executable files such as server Bun, server Go and server Rust. To run this, let's open terminal and for example, to run Rust server, let's run the server Rust. To open this, let's go to our browser and open localhost 7000, which will serve simple hello world. Similarly, to run server Go, I will create new terminal and run server Go. And to run Bun server, I will run server Bun. To benchmark this, I will open a new terminal and use a tool called Bombardier, which is an HTTP benchmarking tool written in Go. So to run Bombardier, the syntax is like this: Bombardier, duration 3 seconds, concurrency of 10,000 and the endpoint. Here I am running the benchmark for Rust server. Here Rust can handle on an average of 3249 requests per second. Similarly, if we benchmark Go, it handles on an average of 2955 requests per second. Finally, we will run the benchmark for bun, which will handle on an average of 2700 requests per second. I know this is not the right way to do benchmarking, but I think it gives a fair idea that bun is somewhat comparable to Rust or Golang in terms of performance. In fact, I have seen few other benchmarking tests performed by other developers. Performance of bun when compared to Rust or Golang is not bad at all. Also, as we discussed earlier, JavaScript together with Bun.js has many other advantages. So we are going ahead with those tools. Apart from language and runtime, for database we will use Postgres because it is feature rich as well as it has JSON support for schemas. Then for local first we will use Electric SQL. It will handle the complex syncing logic between the central server as well as the local database. Then for API we will use OpenAPI standards, and for telemetry we will use OpenTelemetry structure. And for documentation generation, initially we will use simple tools such as TypeDoc. Later we can upgrade to complex tools such as Docusaurus. Now that we have a fair idea of the tech stack and mainly we have finalized the language, we will go ahead and discuss the project structure. Okay, the first section of the framework is app section. These will be the entry points and composition routes. For example, if user wants to start a server, they will be starting the server application. This will be the entry point. Server will require whatever packages it needs and will start the server. Similarly, for example, user wants to start the front-end application. It will be a separate application. The front-end will import whatever packages are needed for the front-end and will run the front-end application. Second is packages section. For example, core package will contain plugin system, hook system, etc. Auth package will contain authentication and authorization system. Logger package will be responsible for structured logging, etc. Next one is plugin section. These are usually third-party plugins which can be installed into the framework. Finally, we have test section where we will have unit integration and E2E tests. That's about it for the architecture and design part. It's time to get our hands dirty. But before we start coding, let's set up our project home on GitHub. I'm creating a new GitHub organization so that everything related to this framework lives in one place. Now, we need a name for this framework. I've been thinking about this and I want something that represents speed and performance. So I'm going with Vega, which means speed in Sanskrita language. Anyway, we can change this later if we want. Now Vega and Vega Web both are also taken. Okay, let's try Vega HQ. Great, it is available. Let me quickly go ahead and enter my email address and complete the remaining steps. Now for the repository itself, we will call it simply Vega with the description a fast offline first web framework. This is where our entire journey will be documented in code. Perfect. Our project now has a home. Time to create our local workspace. Let me navigate to my projects folder and create our Vega directory and cd into Vega. Let's open this in VS Code. Beautiful, a blank slate. First thing first, let me create a readme.md. I'll create this with the basic one with title Vega and save it. Let's git init, stage our changes and make our first commit with message initial commit. This is historic moment number 1. And run git push with set upstream origin main. There we go. Changes are now pushed to GitHub. Now let's quickly create a new branch. Let's name it dev. For development environment, we are setting up a development container. Why? Because I don't want developers to have it works on my machine problems. First, we will create a .dev container folder. This is where Docker will look for our container configuration. Inside, we need a Docker compose YAML file. Let me paste an already prepared content. We are using latest bun docker image here. The sleep infinity command keeps the container running. We are mapping our projects folder to user src app inside the container and exporting port 3000 for our web server. Let's save this. Next, we need a devcontainer.json file. This tells VS Code how to work with our container. The name of the project is Vega Web, port is 3000, remote user is bun. Then we are using Docker Compose file we just created. The service is Vega. The workspace folder is user src app, and shutdown action is stop compose, and we are also adding bun VS Code extension. After these two files are created, hit Shift Command P to bring the command palette and reopen in container. Also, let's make sure that Docker is installed and up and running. Super. Now we are inside our development container. Let's open a terminal and verify bun is working by checking the bun version. Perfect. Time to initialize our project with bun in it. I'll choose a blank template. Great. Bun has created our basic project structure. We get an index.ts file with simple hello via bun message. Let's test it quickly, and yes, it works. But we don't need this index.ts file. Let me delete it and check our package.json. I'll rename the project to Vega and remove the module field because we don't need it. Everything else is fine. Now we start building our project with the monorepo setup. First, let's create an apps folder. This is where our entry points live. Inside that, we also create a server folder with a new file, index.ts. This is the entry point of our server app. Let's add some comments. Create the main server app. This is async function, create app. Inside this, first load the config. Then we will prepare the composition root object, that is const app is equal to an object. Inside this, we will load hooks, logger, etc. Then we will also load factories. Then we will create servers. For example, we will say await create servers. Now, where this server come from? Let's create this inside a package from, let's say, packages/http. Then we will call the main function create app. Okay, now to create this, in the root we will create packages folder. Inside that we will create an HTTP folder and add index.ts. Inside packages HTTP, we create our server factory, that is export function create server. In fact, the packages are located one level deeper. Now this uses bun's built-in serve function. Serve accepts multiple parameters. The first one is port. Then it accepts routes object, where we will define the root route with new response hello world. As a fallback, we will also have a fetch callback which accepts a request parameter that returns a new response. For example, we will say not found. Okay, now we can return the created server, or what we will do is we will assign it to a variable and then we will return the server here. Before that, we will also console log that says server started at server.url.host. Okay, now that creates a server. Okay, we'll make this async. Let's test this. Run bun app server. It says server started at localhost 3000. Let's visit this URL. It says hello world. All right, this is done. Let's close this and create workspace configuration to tell bun that any folder inside package is part of our monorepo workspace. Here we will add workspaces and add packages/star. Once we have this, any folder inside the packages folder is added to the workspace. Next, TypeScript configuration. In tsconfig.json, under compiler options, I am setting base URL to current directory. This ensures we are resolving from the root. For mapping imports, we will add paths. Inside that, we will say whenever there is an import for @vega/star, it should map to an array of paths, that is packages/star. This lets us import @vega/http instead of the relative paths. We will also ensure that we are including the packages with include. Now we will open the server index and instead of packages/http, before that our HTTP package needs its own package.json to be properly recognized. I'm naming it @vega/http. Let's also add module index.ts, type module, and then we will also make it private for now. Let's close this. Here now we will be able to import from @vega/http. Now this is not available. To make HTTP package available, we will run bun install. When we do that, bun automatically links our packages together and the HTTP package should be available now. Now if we run bun/apps/server and if we reload the page, perfect, our modular architecture now is working. As the last step, let's polish some developer experience. I'm adding a script section to our package.json with the dev command that runs cd apps/server and bun index.ts. We will also add the watch flag. Now we can simply run bun dev and get hot reloading. Let's test this by changing our hello world message to simply hello. And there it is, automatic reload. All right, that's it for today. A quick recap. we created a proper GitHub repository, a reproducible development environment with Docker, a monorepo structure, our first working server with hot reload, and the beginning of our modular architecture. Today's video might look simple, but we have actually solved some really complex problems. We have consistent environments, a proper module organization, and a development workflow that will scale as our framework grows. In the next video, we are going to give this server app some real structure. We will add config loading, a proper logging system, our hook system, and a plugin loader. Thanks for watching, and I'll see you in the next one. Namaste.